In the last class, we learned that the Bell's inequality. So let me start by writing that. It was a situation where a pair of particles were created in the entangled state, singlet state, say here, and we observed it at a distance, say, I'll try it here. So suppose it was created here, and uh, things went in the two directions like this. And ultimately you observed it in three possible directions. You observed it in the A direction, some B direction, and some C direction. Here also you observed it in A direction, B direction, and C direction. Okay. So I'll write A, B, and C, and A, B, and C. So effectively what we are doing, Alice is sitting here and Bob is sitting there making the observations. So this fellow is sitting with three Stern-Gerlach instruments, one oriented in this direction. The magnetic field is oriented in this direction. Another magnetic field is oriented in this direction, and third magnetic field is oriented in this direction. And when a particle comes, she can observe in one of these directions. So she arbitrarily chooses one direction, A or B or C, and similarly Bob. So they make their own observations and finally they tally. And we have found yesterday that the probability that the first particle measured by Alice will be up in the A direction, as well as the second particle in the B direction. Second particle means something that is measured by Bob in the B direction, should be smaller than the probability of measuring the first particle in the A direction and the second particle in C direction, plus the first particle in the C direction and second particle in the B direction. And the probabilities can easily be calculated because after they tally their results, they can find out how many times this happened, how many times this happened, how many times this happened, divided by the total number of times gives the probability. So this can easily be checked. And a local realism, that theory predicted this. So this is by local realism. While QM predicted violation at some angles or some angles. So the local realism predicted that this will always be true, while we have seen that quantum mechanics predicted, especially when the angle theta would be small, then this would be violated. This is something that we have seen in the last class, and we proceed from there. We said that actual measurement, actual experiment is not exactly done using this. What is done is using something called the CHSH inequality. And for that, we have defined something called a correlation function. Correlation function uh, for observations at a difference of angle theta, which is, or I can say, sorry, I'll write it this way. If one is oriented at angle theta 1, another is oriented at angle theta 2, theta 1 minus theta 2, this would be, we have seen that this is minus cosine theta 1 minus. So we define a correlation function, and then this is actually, I'll write the names again, Closer, Shimoni, Horn, CH. Shimoni and Holt. They said that let us do the experiment in slightly different way. Alice measured in two possible angles. So Stern-Gerlach apparatus 1 is oriented at, aligned at theta 1 and theta 1 prime, and Stern-Gerlach apparatus 2 aligned at theta 2 and theta 2 prime. Okay, so this fellow has two possibilities to align, either theta or theta 1 prime, theta 1 and theta 1 prime, and this guy has also the possibility of aligning at theta 2 and theta 2 prime. Now, in that case, they showed that if they define the sigma function as C, defined this way, theta 1 minus theta 2 plus the correlation function between theta 1 minus theta 2 prime plus C theta 1 prime minus theta 2. Now this is, the last one is minus C theta 1 prime minus theta 2 prime. Then they showed that the magnitude of this function should be less than equal to 2. Okay. So that is the CHSH inequality. So this is the CHSH inequality, follows from local realism. And they showed that this will be violated for some of these angles, theta 1, theta 2. Okay, that was the setting that I laid down in the last class. Now, the actual experiments are not done by electrons, using electrons or spin half particles. The actual actual experiment was done using photons. And so we need to go back to what we learned about the quantum theory of photons. And on that basis, we need to proceed. So what we learned is that, I'll just draw a line here so that you can. Photons, the polarization, whenever you have a polarizer in front of a light beam coming, which is not oriented in any particular way, the polarizer orients it. So each photon, before falling on the polarizer, has a probability of being any of the polarization states. So it is a linear combination of all possibilities. And as it passes through the polarizer, that collapses into, say, the vertical polarized state. So you have a beam coming. I'll draw the straight line. You have a beam coming, and the beam is falling on a polarizer. and as it passes, it is polarized in the, say, in the vertical direction. And then if you have another polarizer oriented at an angle, so you have another polarizer which is oriented at an angle, then what ultimately goes, a part of it will ultimately go and a part of it will be blocked. And we learned that that is the amount that goes through is cos square theta. That's the Malus law. And we learned that the any state, so any polarization state can be, it's a two-level system because it can be either vertically polarized or horizontally polarized. And the vertical polarized state and the horizontally polarized state, these two are can be treated as the basis vectors, so that any vector can be written as, so a general, I write like this, can be A vertical plus B horizontal. So it can be written like that, with the condition that A square plus B square should be equal to 1, because it has to be, I mean, when you observe it, you observe it either this way or that. So, and we learned that if there is there's a beam which is polarized at a particular angle, theta, then its projection onto the vertical direction will give the probability as cos square theta. So Malus law actually follows from what we have done. So we learned that at any particular angle v, theta was written as cos theta v plus sin theta h, and the horizontal one was, we found it to be, because we expressed it as 90 degree minus cos, so it is minus sin theta v plus cos theta h. So this is something that we have done earlier, just as a way of recapitulation. So in general, all these can be expressed like this. So vertical polarization, polarization, the horizontal polarization, polarization at a particular angle, and the v theta, h theta can also be treated as a different basis vector, set of basis vectors, and any vector can be expressed in terms of the, vertical and horizontal in the theta direction, and all that naturally follows. Now, by the way, there is a certain crystal, calcite crystal, naturally occurring mineral, which can distinguish between the polarization states, vertical and horizontal. So that if I have a crystal like this, no, I'll not draw like this. I'll draw a bit differently. I'll draw like this. Very bad drawing. So that there's a plane something like this. Now, if a beam comes a beam of light comes, then the calcite crystal has the ability of separating out these into two beams like this, so that the vertical one, sorry, the vertical will come here and the horizontal one will come here. So these can be detected by two detectors. So there are ways of sort of splitting the beams depending on the polarization state. Hmm? So these are actually useful in various experiments. So we can actually see how much of it went this way and how much of it went that way. And if there is a light somewhere here which is emitting this, then you will actually see, if you have a calcite crystal, you see two images. And it can be shown that one image is formed by the vertically polarized light, another image is formed by horizontally polarized light. And polarization is actually very, very common. Those who have into photography, they know there are some filters that are polarizing filters. And if there is a reflection in from water in some place, if you use the camera with that polarizing filter, if you rotate it, you can cut down all the reflected light. Scattered light also, if you look at the sky using that polarizing filter and if you rotate it, then you can cut down the light, you can make the sky become more bluer and things like that, which means that the light that comes after the scattering in air, that's also in some ways polarized. So that's polarization. Now let me delete this, get some space. Now, circular polarization, is where the A and B, these are complex numbers, circular and elliptic polarizations are these. So there are two possible ways of circular polarization. Either it is right-handed circular polarization or left-handed circular polarization. So the right-handed circular polarization is, I can write it this way, is it will have a 1 by root 2. It will be, there will be a minus here. It is horizontal plus I vertical, and the left-handed L is 1 by root 2. 1 by root 2 is needed for normalization. It is just H minus I P. Now, with that background, we can go on to the actual description of the experiment. Now, in the experiment that was done by Alain Aspect and his colleagues in Paris, what they did was they took excited calcium and allowed it to go back to the ground state. So when that happens, that excited calcium is in the spin zero state, and when it goes to the ground state, that's also in spin zero state. So whatever photons are emitted, their total spin must be zero. So the total spin zero, it has been found that they go in a circular polarization state. So which means that you have a situation where you have the point where it is emitted, and these are going in two different directions, like this and like that. And by the way, this is our y direction. xz plane is here. Now, if this one goes in a right-handed polarized state, I'm drawing our classical image of the polarization state, and this one would go in a left-handed polarization state. Then if you look at it from the point of view of the y-axis, that means you look at it from this angle, then you see that they are both in the same sense of rotation, which means that they go in opposite directions, but their state is the same. Okay, same polarization state. Now, how do we represent this entangled pair? When I was dealing with the entangled pair in spin half particles, remember what we did? We wrote it in the direct product space, and then after having obtained the 4x4 matrix, we took the eigenvalues and eigenvectors in a attempt to diagonalize that to define new set of basis vectors. And what we found was that the eigenvectors were the possible kind of states, including the entangled states, the singlet and triplet states. Here also we would need to do the same thing, but I'll just skip the state. I'll just state the result of something that is similar to a singlet state in this case. State in this case would be 1 by root 2 of both in, that means this is a positional representation. First one, whatever I write, is the first particle. Second is the position of the second particle, which means that both are vertically polarized, plus both are horizontally polarized. So this turns out to be the singlet state. And as the character of the singlet states are, we have seen in the case of the electron, if you take another angle, which means if you take, say, 1 by root 2 v theta plus h theta, then if you substitute, where is it? Yeah, if you substitute these here and do a bit of algebraic manipulation, you can show that this is equal to this, which means that here also we have the property that independent of the orientation, they have the same state. Okay, that was the one of the characters of singlet state we had earlier identified, and that is carried here, which means that all that we have learned in case of electrons, they can be applied to photons, to this singlet state. And the only difference is that wherever we had theta by 2 in the spin half particles, in spin 1 particles, we have theta. So there was a law, cos square theta by 2 rule. Here we have a cos square theta rule, and so on and so forth. So that's the only difference. Otherwise, it will be more or less the same. So in this case, then, we can define the correlation function. Correlation function, the C of the photon, angle theta, would be the probability of both being in the vertical direction plus the probability of both being in the horizontal direction minus the probability of one, for the first one in the vertical direction, second one in the horizontal direction, minus the probability of the first one in the horizontal direction, second one in the vertical direction. So being similarly polarized minus being differently polarized. That is the correlation function. And in that case, it can be shown in the earlier case, that means in case of spin half particles, we have shown that this would be minus cos theta. But since in this case we have to replace theta by 2 by theta, this turns out to be cos 2 theta. Okay. So that's the only difference. Otherwise, everything's fine. So then what these people, Alain Aspect and his group did was create a pair of entangled particles. They are allowed to go into different directions. Uh, and then you measure their spin in different angles. And in some cases, if you look at it in a particular direction, in some cases they will turn out to be vertically polarized, in some cases they will turn out to be horizontally polarized, and so on and so forth. So you measure. That means here we have essentially two angles, say either this angle or maybe this angle. So it is say theta 1, this angle, and theta 2, theta 1 prime, right? Theta 1 prime of the first one, and second one will again be measured in two possible directions. And this is theta 1, and this is, theta 2, and this is theta 2 prime. I mean, it's not that theta 1 and theta 2 are the same. I mean, they can be, any possible ways. So effectively, I have four possible angles in which this can be measured, and what it is actually following the CHSH prescription, that there would be the SG1 apparatus is oriented at angle theta 1 prime, theta 2 prime. Instead of SG1 apparatus, they simply had polarizers. And how many photons go through, they measure by actually measuring the intensity of light at the other end. That was relatively simpler experiment. So you have this inequality, which should be satisfied if the local realism position is correct. But what they found after doing exactly the same experiment is that they found that under certain angles, this turns out to be bigger than 2. We have earlier seen in the last class that it can go as high as 2 root 2, but here they found that in some angles that can be bigger than 2. The paper was published towards the late 1980s, and after that this experiment has been repeated by many groups, and now a consensus has emerged that the assumptions on the basis of which the local realist position is formulated, that entire assumption cannot be right. So there are two components of the assumption. One is realism. One was local and the other is realism. Sorry, again I'm writing. Local, if you recall, means that action at one place cannot instantaneously affect the measurement at another place. Realism implies that the state that I'm measuring, before measurement, the state had a value. And I have just measured and found out the value. Now we know that both cannot be correct. But the quantum mechanics position is that QM says neither local nor realist. So quantum mechanics actually doesn't, the way quantum mechanics and its Copenhagen interpretation has developed, it actually has abandoned both these positions. While Einstein was uh, actually proposing that both these are true. Now we know that both these together cannot be true because it has contradicted with experiments. And therefore, one possibility is that it is the quantum mechanics position, the Copenhagen interpretation is correct, which means that it is neither local nor realist. The other possibility is one of the thing is correct. That means it is local, but not realism is not valid, or realism is valid and locality is not valid. Now, after that time, much of the work on the foundation of quantum mechanics has developed either assuming locality or assuming realism. But we now know that both together cannot be correct, and therefore, further attempt to develop the local realist position, which is also sometimes called the hidden variable theory, that is more or less now abandoned. But still, attempts are on to develop theories based on either realism or locality. Now, I can tell you that out of the people who are, by the way, the number of people who are working on such foundations of quantum mechanics are relatively small because nobody has contradicted the idea that quantum mechanics, as the mathematical formalism of quantum mechanics, as it is formalized, that is correct. Nobody is contradicting that because it has satisfied all experimental tests. Einstein's only point was that it is not yet complete. We need to know more. It is not yet, there are still loose ends that are to be tied up. And such attempts are on, and the people who are into those attempts, many of them believe that the realism can still be, can still survive, while if you assume that two particles can be entangled, which are not at the same place, that means the situation is that they together have a wave function. And if you observe one, then the wave function collapses. It is not that a signal went from this place to another. It is basically the whole wave function collapsed into one state. So that is the condition. After that, experiments have also been done on entangled triplet of particles, which means three particles that are entangled, three photons that are entangled. In that case, the singlet state is all of them in vertical or all of them in horizontal, the summation of them. So experiments have also been done that has also satisfied the predictions of quantum mechanics. So that is where I would possibly end this lecture.